I'm Seth Kessler, President of Metis Design, and today I'll be talking about our sequential Phase 2 SBIR demonstrating structural health monitoring for naval assets. Metis Design is a small technical consulting firm that offers novel multidisciplinary defense and aerospace solutions. Our core expertise lies in structural health monitoring and multifunctional nano-engineered materials. We have experience from completing more than 50 SBIRs and have successfully transitioned multiple SBIR-derived disruptive technologies through licensing to United Technologies, Analog Devices, and others. Since it is impossible to test structures under every possible configuration of loads and environments, and improbable to model and correctly predict structural degradation, the DoD must use conservative inspection, maintenance, and retirement cycles. Structural health monitoring aims to integrate a network of miniature, non-destructive evaluation equipment in order to facilitate real-time automated inspection and enable condition-based maintenance, or CBM. This SBIR program is specifically targeting the SSNX Future Attack Sub, but this technology is applicable to most DoD sea, land, and air assets. Our work in this SBIR is focused on the Wireless Integrity Sensor Platform, or WISP, which has been a collaborative effort between Metis, Analog Devices, and MIT. WISP was developed as an efficient sensing architecture for enabling CBM strategies. It uses a distribution of small and lightweight hardware that can be easily integrated or retrofit into DoD assets without any ties into system power or data. It is compatible with most commercial off-the-shelf analog and digital sensors, in addition to a growing portfolio of advanced nano-engineered sensors, such as those used for measuring fatigue cracks and corrosivity. The standalone version, WISP Solo, directly integrates a sensor with miniature hardware without any cables or connectors. A magnetically coupled reader unit is then used to wirelessly transfer power and data on demand. The network version can daisy chain up to 64 edge devices with mix and match sensors along a 100-foot serial bus, with a single base unit for wireless power and data transmission using the reader unit. Each of the hardware units is presently about a square inch and a quarter-inch tall, with development underway with Analog Devices for a system on a chip that will reduce hardware volume by an order of magnitude. The hardware has successfully passed all environmental airworthiness testing, including for shock and vibration at 20 G, temperatures between -65 and 125 C, and common chemical exposure. The handheld WISP reader is powered over USB and magnetically couples to the WISP Solo or base unit to power the system and retrieve data over a secure Bluetooth Low Energy connection that has been approved by Navy and Air Force cybersecurity authorities. Drivers have been written for Windows, Android, and iOS, and data collection only takes a couple seconds per sensor. Our most mature advanced nano-engineered sensor is the WISP fatigue crack gauge. This sensor is produced by laminating a CNT-based polymer nanocomposite and bonding it to a structure like a strain gauge. As a crack grows in the structure, it tears the intimately bonded gauge, thus permanently increasing its electrical resistance. Since the sensor elements are nanoscale, even if the crack is closed, the network resistance is not restored. Thus, it is completely passive, capable of encoding crack length without any power necessary except when retrieving data. The current production sensor is about a ½ inch square and 0.008 of an inch thick. As compared to conventional foil gauges, our CNT sensor is much more durable under fatigue loads, not susceptible to corrosion, and offers a continuous response rather than preset step values. Through a parallel AFWERX Phase 2 SBIR program, we have been working to establish the detection sensitivity of the WISP Solo and crack gauge by testing hundreds of fatigue specimens. As can be seen in this example plot, the sensor response is fairly linear and accurate with respect to predicted crack length, using a very simple formula that just relates crack length to the square root of resistance change times a geometric gauge factor. The A9095, or the smallest crack that would be detected 90% of the time with 95% confidence, has been determined to be 1/3 of a millimeter, or about 10,000ths of an inch, by two consulting statisticians. Both the TRL and MRL of this technology is a 7 at this point. We have tested the WISP technology at sea on a Navy destroyer and through flight testing on an F-15 with the Air Force. WISP was exclusively licensed to Analog Devices in 2020, who now have production lines running for both the hardware and fatigue crack sensor, with the corrosion gauge expected in 2023 and the single chip solution in 2024. To summarize the system benefits, WISP is a small, lightweight, distributed inspection architecture capable of detecting extremely small cracks with a high degree of confidence without any power. Implementing WISP would minimize manual scheduled inspections for many structures and aid with planning maintenance logistics. It is particularly well suited for locations that are difficult to access or require frequent inspection, and overall will contribute to increased asset availability while lowering operation costs. We seek additional programs of record that are interested in field testing the WISP system for their application. We can deploy the existing system or develop custom sensor sizes, shapes, and/or functions depending on program pain points. We would also like to work more on software and database interfaces to better integrate the sensor output with DoD maintenance logistics systems to maximize the potential for CBM. I thank you for your time listening to this briefing, and please do not hesitate to reach out to me if you have any questions or would like to evaluate WISP for your application.